So, quick question for you here. P hat, what's that stand for? Sample proportion. Sample proportion. And that estimates P, the population proportion. So one of them is a statistic, one of them is a population parameter. The reason we take surveys is because we're trying to find out information about the population parameter. But if you take, repeated surveys, you're going to get different answers. It's just going to depend based on luck as to who shows up in your survey. You can see that even in major surveys. So trying to stay current here, let's take a look at the most recent surveys of job approval ratings. These have slightly different results. All right, they're similar, but they're slightly different. If you know, let's see, this one doesn't show it. Let me just see if we can't find another one. Let's look at Congress. Job ratings, Congress, job. The one thing I wanted to show you here is that these polls have a margin of error, plus or minus that little bit. We practiced some of this the other day, calculating that margin for error. So let's revisit that with population proportions. That margin for error, P hat, plus or minus E, that form of E, your margin of error, looks like this. E is Z sub alpha over 2 times the square root of P hat times Q hat over N. Now, P hat is your sample proportion. That's just going to be X over N for your particular value of P hat. That's going to be your point estimate. Then you surround it by this confidence interval. Z sub alpha over 2, or just Z sub alpha. Let's start with that. Z sub alpha. That's going to be the point on the normal distribution with an area of alpha in the right tail. So, right here in the right tail, the total area is going to equal alpha. Now, unfortunately, that kind of puts it at odds with a lot of the way our technology works. Our graphing calculators, statdisk, Google Sheets, all give you the area in the left tail. So if you want to find this, you're going to have to do, say, 1 minus a particular number. But that's area equal to alpha. Now, what you're doing with this alpha over 2 is really you're making that area even smaller. It's still an area in the right tail. It's just that you're dividing that area by 2. For example, suppose you wanted to find this term for a 96% confidence level. 96% confidence level. Let me remind you that you can calculate alpha, as 100 minus the confidence level percent. So in our case, 100 minus 96 gives you 4, or we'd have a 4% or 0.04 value for alpha. Using this formula then, the Z sub alpha over 2, if you're to try and use that to find a margin of error, the first thing we need to do is calculate Z sub alpha over 2. So let's do that. Z sub alpha over 2 is going to be Z sub 0.04 over 2, or Z sub 0.02. This is going to be the point in the Z distribution with 2% of the area in the right tail. Let's see if we can't find those values from our graphing calculator or statdisk or Google, etc. Let's work on all of them. We'll start with the graphing calculators. So hit the second key, then distribution, or second key, then on the face of it, it'll say vars. We want the inverse normal. It's going to ask you for the area. That's going to be the area in the left tail. If I want 2% of the area in the right tail, how much is going to be in the left tail? 98%. So we'll type in 0.98. The mean of this distribution is 0. Its standard deviation is 1. So you should get about 2.0537. Okay, great. So z sub alpha over 2, z sub 0.02 is 2.0537. Let's see that calculation in a couple other mediums. Let's do it on Google Sheets. So on Google Sheets, here it is. It's norm inverse. And then again, you type the area in the left tail, the mean, and then the standard deviation. So it's an identical calculation to what we did with our graphing calculator. The only difference is the name. Instead of inverse norm, it's norm inverse. Okay. One way or another, you should be able to get that value. Let's do one last one here. You can do that on statdisk. If you go to analysis, then probability distributions, it's pretty nice. It says cumulative area from the left. So again, you're working with the area to the left. Just type in 0.98 and click evaluate. Nice. So same 3 in all of them. But that calculation is part of something bigger, and that is finding a confidence interval. The good news for us is that we're going to let a lot of our technology do the work for us. So we'll start out with problem number 18. So this is section 7.1 still. Let's take a look back at problem number 18. There we go. One of Mendel's famous genetics experiments yielded 580 peas, with 428 of them green, 152 of them yellow, finding 99% confidence interval for the estimate of the percentage of green peas. So we don't necessarily know, in theory, how many exactly to expect, at least for us right here, but we can construct a 99% confidence interval. So let's do that. Let's write down a few relevant pieces of information. So those pieces of information would include that we had X was 428 successes, that is 428 green peas. I'm not sure that's a success. I'll have to talk to Dr. Seuss on that one, maybe. Let's see, how can I get rid of this? There. So X equals 428. N was 580. And we want a 99% confidence interval. What that means is that alpha is going to be 0.01 or 1%. I don't know that we're going to need that value directly in this one, but it does mean that alpha is 1%. Let's do it on our graphing calculator first. You're going to go to Stat, and then to Test, and then to Selection A, which is a 1 proportion Z interval. So those are the keys you're going to type. Stat over to Test, and then Selection A. Now you can just use the down arrow to get down to Selection A. I cheat a little bit. I hit the alpha key, and then just type the letter A, which is right here above the math key. So it has the same effect. one proportion Z interval. So there was 428 successes out of 580 total. Our confidence level is 0.99. And boom, pretty nice. Really quickly, we get out a nice number for our confidence interval. So it's going to be between 0.6909 and 0.7850 is your confidence interval. Now that's for the graphing calculator. What if we did it, say, on statdisk? Let's take a look at it there. Let's clear out this stuff. Clear that. Let's go to analysis, then confidence intervals. We want a one proportion, proportion one sample. 95% confidence interval, 580 was the N, and we had 428 successes. And then click evaluate. Nice. You're getting the exact same confidence interval. I must have typed in something wrong. 0.99. There we go. 0.99. Now we get the exact same confidence interval. Be careful, the confidence interval that you want is this one right here. It's not the one down below. I'm not sure, but my guess is this is what's called a non-parametric confidence interval. I'd have to double check on that, but this is the confidence interval that we want. The important thing, though, with technology is now that it's so easy to get these numbers is to interpret them. So let's talk about the interpretation. What does this mean? Well, it means, and I want you to write this down verbatim. We can be 99% confident that the true population proportion of green peas is between 69.09 and 78.50%. So what's it saying is, well, we don't really know what that population proportion is, but we're pretty sure it's in this interval. We're 99% confident. Now be careful not to call that a probability, because it's not a probability. We'll talk about exactly what this is and what that level of confidence represents in a little bit. But right now, this is our confidence interval, and that's how I'd like you to state your conclusion. These are words that are a little bit more easy to understand for somebody outside of a statistics course. Are we okay so far here? Now, the follow-up question to this is, based on the theory of genetics, Mendel expected 75% of the offspring peas would be green. Given that percentage of offspring green peas is not 75%, do the results contradict Mendel's theory? Well, let's see here. 428 divided by 580 was 73.79%. That's not 75%. That's clear. But do our results necessarily contradict Mendel's theory? Why or why not? Is that a contradiction in Mendel's theory? He expected 75%. Yeah, so the thing is, we constructed a confidence interval. And this is just our best guess of where that percentage is. But because if we did this experiment again, we know we'd get different results, we construct a confidence interval. We say, well, we're pretty sure that the true population is going to be in here. True population proportion is going to be in here. And since 75% is in there, it is in that interval, it doesn't contradict Mendel's experiment or his expected results of 75%. In fact, it falls nicely within there. So it's not a contradiction. But let's go back now and understand a little bit more about this percentage. That 99% is not a probability. It's a level of confidence. What it's saying is that if we did this experiment 100 times, 99 times, the confidence interval that we create would actually contain the population parameter. 99 times it would contain it, one time it wouldn't. So that's what it's saying. At this point, this interval either does or does not contain the population parameter. We don't know what the answer is, unless you happen to know the population parameter. So if you wanted to say something about a probability, the probability would either be a 0 or a 1. Those are the only probabilities that are appropriate for talking about that confidence interval. But we can have a level of confidence in our procedure. And that's what that 99% reflects. Is that, 99 times out of 100, this will contain the population parameter. All right. Let's do another one. Let's do an interactive one. Sort of interactive, right? Going back to a tried and true method here. M&Ms. All right. I think it's Charbel wanting to say, oh, cool. You need a volunteer? You need a volunteer? All right. Maybe. We'll see. We'll see. But let's do a little experiment and try and calculate how many, or the percentage of, certain colors of M&Ms that we get out of this bag. Try and estimate the true population proportion of, say, blue M&Ms. Okay. So, let's spread them all out. Now, what's true is that 99% of the time, or I'll let you pick it, typical values for a level of confidence would be 95% or 99%. Those are going to be your typical values. You're not going to see things outside of that very often. Green, brown, and wow, that one's folded. I'm not even sure I should count that one, but I guess we will. Yellow. Come on. All right. If this was a hockey puck, I'd have much more grace with it, but I don't practice with M&Ms very often. There. And didn't get too many red ones, did we? Okay, so let's see how we did. Now we can kind of compare things to our to my morning class. I did that for my morning class as well. And let's see, where did those results go? Yeah, here we go. So these were the results from my morning class. Let's see how we did in comparison. So orange, we got 7 orange ones. 7 orange, 5 yellow, 2, 4, 6, 8, 9 brown, 6 red, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 blue, and 2, 4, 6, 8, 10, 12, 14, 16 green. All right, so let's see how many is that. That's going to be 12, 21, plus 19 is 40, 56 again. So pretty consistent for M&M Mars, 56 M&Ms in both of these. Let's find a confidence interval for the proportion of blue ones. So blue. So P hat is going to be 13 out of 56, at least for this class. It was a little bit different from my last class. 13 out of 56. Let's see, what level of confidence do we want? 95%? That's your standard one. That's where most people are going to be at, a 95% confidence interval. So what that's saying is that 95 times out of 100, this procedure will contain that true population parameter. So let's do that. I'm going to do it on my graphing calculator here. So go to Stat, over to Test, then down, all the way down to A. We had 13 blue ones out of a total of 56. I want a 95% confidence interval. So our confidence interval is between 0.1216, call it, and 0.3427. So unless you're M&M Mars, you don't know what that true population parameter is. Although we'll look it up in a second. But what you're saying is, if you were just a student in a stat class, is you can say we can be 95% confident that the true proportion of blue M&Ms is between 12.16 and 34.27%. So kind of a wide confidence interval. I mean, you're giving yourself a lot of room for error, but whatever the true proportion is, we think that's it. Now our best guess for that proportion is 13 divided by 56, so it's about 23%, roughly speaking. That's where we think things are. Let's see how we actually did in comparison to the actual true value. So let's just Google that real quick. Proportion of M&M. True proportion of blue M&Ms. Okay, so 24% is that true population proportion. Does that contradict our results at all? No, because 24% is right in here. And actually, we were pretty close to 24% with our own sample estimate. Maybe what we'll do a little bit later is kind of pool both of these and see what happens. Okay. How are we looking on this one? Proportion of M&Ms. All right, blue ones. Charbel, hungry this morning? Good man. I knew I could count on you. I wanted to ride my bike as far this afternoon. All right. Let's do a few more here. We'll start with problem number 18. No, sorry. We'll continue with problem. We already did 18. We'll do 20. So the drug OxyContin is used to treat pain, but it's dangerous because it's addictive and can be lethal. In trials, 227 subjects were treated with OxyContin, and 52 of them developed nausea. Construct a 95% confidence interval estimate of the percentage of OxyContin users who develop nausea. So this time I'll do this one on statdisk, just to kind of give you some variety. You can also do it on your graphing calculator. Starting to kind of recommend / push a little bit that you use statdisk. It's just nice and convenient. But you know other graphing calculators too. Maybe it's not a bad idea to be familiar with both. So let's write down some relevant information. We had 227 users, 52 of them developed nausea. So n equals 227, x was 52. We want to find a 95% confidence interval So let's see about that. We'll do it in statdisk this time. Close this last one out. Go over to analysis and confidence intervals. Over to proportion, one sample. 95%, we're okay there. This time we had a sample size of 227, of which 52 of them developed nausea. The one thing that's nice about statdisk is it actually gives you this margin of error. E is a little bit more than 5%, 5.4%. Okay. So let's see. Our confidence interval is our confidence interval is between 17.4% and 28.37%. So let's write those down. 0.1744 to 0.2837. Now let's also write down E as well. E is 0.05467. Okay. Let's keep in mind what this is. That really represents p hat minus E to p hat plus E. So that's one way to write your confidence interval. And that's typically what we're going to do. It's what you'll see me do a lot. But what I want you to do is state your conclusion in words. What is this saying about the proportion of OxyContin users who develop nausea? Does anyone want to give it a shot, put their conclusion in words? Sir? Perfect. We can be 95% confident that the true proportion of people who develop nausea using oxycodone is between 17.44 and 28.37%. Perfect. So it's kind of like a little format here. We can be 90, blank percent confident that the true proportion of blank is between blank and blank. So this is something that you should get down pretty carefully. Stating your conclusions is something that I want to emphasize a little bit more in this course than I have in the past, because in the past, the work has been getting these numbers. It was a lot of work because you had to look up z sub alpha over 2. Remember, your term for the error is this. E was z sub alpha over 2 times the square root of p hat times q hat over n. And then you'd have to do this calculation, the p hat minus e to p hat plus e. It was a lot of work. We just get all that stuff at the push of a button. So where I'm going to place the emphasis is finding or stating the conclusion. So please be comfortable with that as you're working through this. There's a part B to this. Are we okay with part A, our conclusion here? Let's take a look at part B. It says, compare the results from part A to a 95% confidence interval for 5 subjects who developed nausea amongst the 45 subjects given a placebo. Do you understand what a placebo is? Kind of a fake treatment. So ideally, when you're doing a test of a drug to see if there is an effect, you want to eliminate psychological effects that, oh, well, I'm getting a drug, I should get better. So you give people a placebo. You give it to them at random. And it's basically kind of like a sugar pill. It has no effect on a person's health. But they may have a psychological boost. In any case, the percentage of subjects given a placebo that developed nausea is between 1.93% and 20.3%. So let me put some numbers here down on a number line. 1.93% and 20.3%. That's our confidence interval for the people who develop nausea while taking a placebo. So somewhere in here. And then there was our confidence interval for the people who got oxycodone. That was somewhere between 17.44% and 28.37%. So that interval's here. The question is to compare these two intervals and come up with a conclusion. Are these necessarily different proportions? Is the proportion of people who develop nausea using oxycodone different than people who develop nausea just because? Are those two different proportions? And they could be, but do they have to be? What's happening in this little interval right here? They overlap. So the percentage of people who develop nausea just because could be in here. And the same thing is true with oxycodone users. It could be in that interval as well. So what it's saying is that these are not necessarily different proportions. They could be, they could be the same. We can't conclude that these two groups are different on that one characteristic. Basically it's saying, well, we can't necessarily conclude that oxycodone causes you to be more nauseous than not taking it. That's what it's saying. Not that I necessarily recommend taking it, it's just that nausea doesn't appear to be one of the adverse effects, is what you can conclude from this. Let's go back and take a look at our M&M's example. And let's just modify things a little bit. Let's do our totals for this experiment. So let me create another column here that reflects the totals. So it'd be 13, 10, 15, 17, 28, and 29, and then 112. What do you think is going to happen if I now create a confidence interval for the proportion of blue M&Ms? Is that confidence interval going to get wider or smaller? Or it's going to stay pretty much the same because it's, you know, not a whole lot different working with this sample as opposed to the combined sample. Any predictions? Well, let's see. So we've got a new x and a new n. So p hat is going to be x over n, which is going to be 28 over 112. Let's run through the numbers here and see what difference that makes. So I'll go back to my graphing calculator, stat, over to test, hit the alpha key, then the math key is a quick way to jump to this. We had 28 successes out of 112 possible M&Ms, and we want a 95% confidence level. So this time we get between 0.1698 and 0.3302. Let's compare that to our previous interval. Our previous interval is right here. So instead of being between 12.16% and 34%, we've got 16.98% to 33.02%. What happened to the width of our interval? It shrunk, right? It's not as wide. And the reason it's not as wide is because we have a larger sample size. The more you sample, the more information you have, the more confident you are about what that true population parameter should be. And we're seeing just that. When they do national elections, surveys for those are 1,000 or 2,000 at most. They're pretty good about that stuff. But adding more people or more samples, we got a much narrower confidence interval. I mean, look at this. This is like about 5% narrower on both ends, right? Instead of 12, we're at close to 17. Let's just take a quick look here. 28 divided by 112. We got, well, that's exactly 0.25. That's pretty close to the accepted true value, at least the one that M&M's publishes, which is what, 24%? So our estimate was pretty good, but it's just an estimate. And we surround it by a confidence interval saying, yeah, we're pretty confident. So adding more to the sample size decreased that window. Sometimes you want to reverse engineer this. Sometimes you're like, you know what? I want to be within 2% or 4% or whatever. Instead of here, you know, I've got a margin of error of about 5%. Actually, what? No, 8%. I might want to control that and make that smaller. So let's see if we can't do that. In fact, you can do that. And what you need to do is you need to adjust the sample size because your error term looks like this, that E term. And if you adjust your sample size, we can make this sample big enough to control that error. Now there's two possibilities for controlling that error. Depends on what you know. If you don't know anything about your experiment, then you use one. If you know some stuff about your experiment, you use the other one. I think the formulas for this are on page 307. Yeah. So let's take a quick look at those formulas. They're right here on page 307. But let me write them down and talk about them a little bit. So, sample size calculations. Now, you should probably pay attention to this one fairly closely because your graphing calculator, Google Sheets, and statdisk aren't going to bail you out on this one. There's no quick fix for finding this stuff. So, one formula is n equals z sub alpha over 2 squared times p hat times q hat over e squared. E is just how close you want to be. You want your sample estimate to be within 2%? Okay, that's going to be your E, 0.02. This assumes that p hat is known. And that is an estimate of the true population, or an estimate of the population proportion based on maybe a previous study. If you don't know p hat, if you don't have an estimate from a previous study, then you're going to replace this part with the number 0.25. 0.25 is kind of like a worst case scenario. It's assuming that p hat and q hat are both 0.5. That should be squared as well. So let's practice this with problem number 34. Let me remark here is E is the error, and z sub alpha over 2 is just as it was earlier. That is the point in your standard normal curve with alpha over 2 of the area in the right tail. I'm frankly a little astounded by this, but I don't know. It says a sociologist plans to conduct a survey to estimate the percentage of adults who believe in astrology. How many people must be surveyed if we want a 99% level of confidence and a margin of error of 4 percentage points? So, okay, how many people should we put in our survey? Let's find out. This is problem 34A. We wanted a 99% confidence level. Now here we're going to actually have to determine what alpha is. If we have a 99% confidence level, what's that mean alpha equals? Yeah, 0.01 or 1%. So alpha is 1% equals 0.01. And from there I need z sub alpha over 2, which is z sub 0.01 over 2. Now you're taking that 1% error and dividing it up into 2 tails, or 1% of the area. So it's going to be z sub 0.005. We need to find that. Keep in mind what that is. That's the point. That's a really terrible normal curve, my bad. Sorry about that. That's the point on the standard normal curve with 5%, or 1/2 of 1% of the area in the right tail. And I've said it before, unfortunately that's not the way your Google Sheets works or your graphing calculator. Graphing calculator works with the area in the left tail. What number should I be putting in for my normal inverse or inverse normal? 0.995. So 1 minus 0.005 gives me 0.995. So find that number from your graphing calculator or from statdisk or wherever. probably. Lauren, what'd you get? Well, we don't want a confidence interval. We just want the z value. So you go to analysis, probability distribution, and then normal distribution. So if you're doing it on statdisk, again, we want the area to the left. What's that area to the left? 0.995. So it should give me 2.575 something. All right. Are you able to get that on whatever technology of choice that you're using? All right. And it's really important that you can. So if you're not comfortable, this is a good place to get some help. Good? All right. Bernay? Good? Kendrick? Good? All right. All right. No dissent. So 2.575. So that's your z value. Good. And I think that gives us pretty much all that we're going to need to know. So for part A and B here, really, our error is going to be 4%, or 0.04. We know what z is. Z sub alpha over 2 for us in this particular case is 2.575. So let's find n. That's going to be 2.575 squared times, let's see, they didn't tell us in this particular part what p hat was or q hat, so we have to use the second of these formulas, 0.25 divided by 0.04 squared. Let's put that into our calculators. 2.575. Hit the squared key on the left-hand side. Squared, right down here, the x squared key, times 0.25 divided by 0.04, and then again hit the squared key. Now there's something peculiar that I'm going to ask you to do. It's only worth 1 point, but I am going to ask you to do it. In being conservative, since this didn't land on an exact number, an exact integer, and you can't poll 1,036.035 people, round up. I know that if in normal circumstances you would round to the nearest integer, but in the case of sample size calculations, you always round up. It's just being a little bit more conservative in your approach to this. So we get 1,036.035, etc. And we'll round that up to 1,037. So that should be our sample size in part A. In part B, they tell you, okay, let's use information from a previous survey which had 26 respondents said that they believed in astrology. And this is the part that surprised me earlier. 26% believe in astrology. I just don't think it's that high, but whatever. In this case, we're going to use a different formula. We're going to use this one because we have a p hat that we kind of know from a previous survey. The z will still be the same, 0.2575 squared. But they tell us that p hat is 0.26. What's q hat going to be? If p hat is 0.26, what's q hat going to be? Angela, thank you. 0.74. Q hat is 1 minus p hat. Let's put this one in our calculator and compare it to our results from the previous one. Knowing some information is going to help us out a lot in this one, I think. So 2.575 squared times 0.26 times 0.7 or 0.26 times 0.74 divided by 0.04 squared. Nice. Sarah? Yeah. So the where that was given was right here. We wanted an error of 4 percentage points. So yeah, that's what gave us your E equals 0.04. Okay? No, I appreciate the question. Thank you. All right. So what should be my N in this case? Thank you, Nick. 798. Remember, you always round up. So 798 for our sample size. That's part B. Yeah. Okay on that one? All right. For homework, in either edition, do problems 1 through 35. So 12th or 13th edition, do 1 through 35. Yes?